Hello, this is Miss Nichols, and we are in our electrostatics unit of Advanced in AP Physics 2. The topic of this lecture is work and electric energy. And the essential question is, how do we store energy in the configuration of a system of charged objects? So just like moving objects around in a gravitational field requires work and can change the gravitational potential energy of an object, moving charged objects around in an electrical field can change the amount of electrical energy stored in the system of electrically charged objects. It does, though, depend on the direction that you move things, because remember, on this cup, for example, moving it from here to here actually doesn't change its gravitational potential energy, but moving it by the same distance from here to here does. So the amount of movement and also the direction of that movement matter when it comes to changing the potential energy stored in systems of masses or charges. So for example, if you imagine we had a small positive test charge like a proton, and we start it at that location marked by the yellow star, and then we move that proton along the path marked 1, 2, 3, and 4, some of those movement chunks will require work or will release work to the outside world, and some of those movement chunks won't. Because like charges repel each other, taking a proton from the star and forcing it to go closer to that source charge indicated by the big positive sign requires positive work. It requires an outside force to add energy to that system. Pushing two objects of similar charges closer together is requiring energy, and so two similarly charged objects close to each other store up electrical energy because they don't really want to be there. So we're going to say that, moving like charges together results in positive work and a higher energy system overall. Moving that proton along path number 2, on the other hand, actually does no work because I'm not forcing those two positively charged objects to get any closer or any further than they already were. And that means that the force and the distance moved are always perpendicular to each other, and by definition, that's actually zero work. Path 3, on the other hand, in this example, is going to represent negative work, which means that the charge itself can do work on the world, or we can take energy out of our system, because moving two similarly charged objects further apart is kind of the way they want to go. The force is pushing in the same direction that you're moving. And so that means we're reducing the total energy in the system and transferring that energy out of the system somehow. Path 4, moving back to the star, is going to be a zero work path for the same reasons that path 2 was zero. The distance between the charged objects is staying constant. A quick note about this: if we switched our test charge for a negative test charge, or we switch our source charge for a negative source charge, then the signs of the work are all going to be reversed. So in other words, taking two oppositely charged objects and allowing them to move closer together is actually negative work because they want to do that. And pulling two oppositely charged charges apart is going to be positive work, so we could store energy in a system by separating opposite charges or by compressing like charges. So calculating work, usually when I start thinking about work, I start with this universal equation for all kinds of work. It applies for every force and every application of work that we've been dealing with, and that is in your equation sheet. It's got two pieces in there. Delta E equals W. That piece says that work will cause an object's energy to change for positive or for negative, and that we can calculate work always by the amount of force exerted on the object multiplied by the distance the object moves parallel to that force. Okay, so moving in line either towards or away the direction of the force, but not sideways to the force. The problem with using this equation regularly in this particular unit is that because of our limitations of not using calculus, we can only use this particular equation when the force is a constant value. And the only time in electrostatics where we actually have an electric force that isn't changing, normally the electric force changes as you get further or closer from the source charge. So the only situation that we really have a constant electric force as an object is moving is when that object is in a uniform electric field, like you might find in between two parallel plates. So we'll come back to this later on, but this particular equation only could be used if the force was constant. So I've got that parallel plate set up here, and a note about using this equation with these parallel plates. You would only be using the distance component parallel to the force. So if we had an object at location A and we moved it to location B, then we'd use the force that we would have from that uniform field, and the distance would be 0.5 meters because we're moving parallel to that force. But if I started it at location A and moved to location P, that distance would also be 0.5 meters because I'm only interested in the distance component that is parallel to the force, and the force goes directly from one plate to the other. If you took an object and move it from A to D, we actually would have 0 meters of distance in my equation, which would mean that the work is going to be 0 because we didn't actually move parallel to the force at all. So the amount of work done on an object is equal to the change of that object's energy. That's from a previous slide. But sometimes in this unit we want to be able to calculate kind of an absolute amount of electrical potential energy, or U sub E. So remember that U is a variable sometimes used to represent energy. I wish they used E all the time, but U specifically refers to potential energy, so we see that for the gravitational energy equation as well, and the subscript E indicates that we're specifically talking about gravitation or electrical potential energy. The units of U are going to be joules, just like every other kind of energy. And while the absolute amount of any kind of potential energy doesn't really have meaning, we still are going to set up some sort of convention or protocol just so that scientists worldwide are talking about the same thing when they talk about U sub E. So a couple notes. Number one, U sub E can only be defined in the context of a system of charges. An individual charge cannot contain electrical potential energy because energy only happens when work occurs, and moving an individual charge around all by itself because you're not pushing or pulling against any forces doesn't really do anything. So UE is always stored in a system of charges, and we need to find a way to define what is 0 energy for a system of charges. So scientists have decided that it makes sense for 0 energy to be the state when two charges are an infinite distance apart, no matter what those two charges are. So what you can see in my diagram below is I have a source charge of some kind on the left, and I have a positive test charge that is an infinite distance apart. And so we're going to say that that system of those charges has 0 joules of energy when they're that far apart. Same thing would be true if my source charge was positive and my test charge is negative, as shown in the little blue negative charge at the bottom of the screen. Now, the reason why it's useful to define that 0 is because when we move those test charges now relative to the source charge, now we can meaningfully talk about the amount of energy that those charges have. For example, when I move that positive test charge towards the source charge, right, we knew that that required work to do that, and so the electrical potential energy of the system containing those two charges is now going to be defined as positive because we added energy to the system by forcing those charges together. Likewise, or oppositely, I suppose, if you take a negative object from infinity and you move it towards the source charge that's positive, the UE of that system would now have to be defined as negative because it released energy or work doing that. Because those two charges wanted to be close to each other. So electrical potential energy can be 0 if two objects are an infinite distance apart. It can be positive, or it can be negative, and that is a little bit different than gravitational potential energy, which is always only positive, because we have this interesting attract or repel situation. So energy is a scalar quantity. We don't have a direction for that energy, but we can define energy as positive or negative depending on how much work was given off or required to get the charges into that particular configuration. Sometimes we deal with more than 2 objects in a configuration. So if I take 3 negative charges and I move them into a configuration that is closer than it was before, well, like charges did not want to get closer together, so that must be a positive work on that system, telling me that the UE of that system is going to go up, or delta UE, which is the same as work, would be a positive value. Everything, of course, would be reversed if I did the opposite and took those similar charges and separated them further. That would be negative work, etc. And of course, if I have a situation where I have opposite or unlike charges and I allow them to move into a configuration where they're closer together, that is something that they sort of want to do. The force does that on its own, which means that we can take energy out of the system. Negative work is done, or work is released by the system. And that means the electrical potential energy of the system is going to go down, or delta UE for the system is negative. You also could have a situation where you take a charge and you move it closer to a like charge and at the same time closer to a opposite charge. So it's going to require positive work to get closer to the negative charge in this case, but it's negative work to move closer to the positive charge. So if you happen to do it exactly right, you could have a changing configuration of a system of objects where the overall work would still be 0, because the positive work could exactly cancel out the negative work in some cases. If you happen to run into one of these scenarios, the electric potential energy of the system is going to be constant, and the delta electric potential energy is, of course, 0. So work is 0. So I want to define a new variable here. This is a word I'm sure you've heard before, but really getting familiar and comfortable with this variable is going to be key to understanding electrostatics and also key in our next unit of electrodynamics or circuits. So this new variable is called voltage. Now, one of the really challenging things about voltage is that it has quite a few synonyms, and you'll see it kind of addressed different ways. The main one that you'll see is that voltage is often called potential. Potential means the same thing as voltage, but that's different than potential energy. Okay, so if the word's energy in there, we're talking about UE, but if it just says potential, then it's talking about voltage. So make sure that you get that down in your notes because it can be really confusing. Regardless of whether we use voltage or potential, the variable that we're going to use to represent this variable in an equation is capital V, and the units of potential are joules per coulomb, which is the same as a volt, which is also a capital V. So this is the only variable in physics where the variable and the unit can be the same letter. You might say like V equals 9V, which is kind of convenient. So the definition of voltage or potential is the electric energy per coulomb of test charge at a point in space. So voltage, kind of similar to electric field, changes space around an object, and we define the amount of voltage as sort of how much that space is warped and how much it would affect an object put at that location in space. Voltage, because it's similar to energy, is a scalar property, which means voltage doesn't have any direction, up, down, left, or right. We don't use those words in voltage. It doesn't have any relevance. However, voltage can be positive or negative, just like we talked about with the electric energy in the last slide. So let's just say for the point of argument that we could measure the voltage at a point in space, which we can. We have a tool called a voltmeter that lets us measure how much electric energy a coulomb of test charge would have if I stuck it anywhere in the universe. And let's just say we took our special voltage measuring meter and we measured the voltage at 5 points in space, and we discovered that the voltage at each of those points was 20 volts. And then we took our voltmeter and measured it at 5 more points that are marked in blue and found the voltage at each of those points was 5 volts. One of the things that we often want to do is make kind of a map so we can visualize the voltage over the course of some sort of space, some two-dimensional space. And so what you often will see is like topographic lines drawn to connect regions that have the same voltage. These lines are known as equipotential lines because equa means the same and potential, of course, means voltage. So this is a line that basically connects points in space where the potential is the same, so I can kind of visualize in the entire system of space what the energy per charge would look like. So that's an equipotential line for 20 volts and another equipotential line for 5 volts. So what is the significance of these voltage values and these equipotential lines that I've drawn? Well, if I grab, and we're going to talk about where do they come from in a minute, the source of a voltage in a point of space, but let's just say we know that this exists, and we're going to go then outside of our system and grab some kind of test charge and bring it into our system and stick it at those points in space that we already know have a certain voltage value. So if I grab a random negative 3 coulomb object and stick it somewhere on my 20 volt line, I can now figure out how much electric potential energy that object basically contains based on the fact that I stuck it in that point of space. So that is not the object that caused the voltage in the space. We're going to come back to that in a minute, but is an object that is basically experiencing the voltage by being put in that point in space. So because voltage is defined as energy per coulomb of chest charge, the electric energy of a negative 3 coulomb charge on a 20 volt potential would be negative 60 joules. It's 20 joules per coulomb, and there's negative 3 coulombs, so that's negative 60. If I then decided to move my little test charge from one spot to another spot while staying on that 20 volt potential, and then I calculated my electric energy again, you'd find the same amount of electric energy. It's 20 joules per coulomb multiplied by negative 3 coulombs. We're going to have still negative 60 joules of energy. So in other words, moving an object, a charged object, along an equipotential line takes no work. Its energy doesn't change. That's just like taking my coffee cup and moving it along an equigravitational line. Even though it's moving, I'm not actually changing the gravitational energy. Same way I'm not changing the electrical energy of this test charge. However, if I move that object from one equipotential line to another, so if I move it from the 20 volt line to the 5 volt line, it now has a different amount of electric potential energy. 5 volts means that every coulomb of charge, test charge, gets 5 joules of energy. So if we have negative 3 coulombs of charge, we're going to have negative 15 joules of energy. And so hopefully you would realize pretty quickly that since the energy of that system is changing, some work is occurring. Because work is defined as a change in energy, and that anytime you move an object from one equipotential line to another, we are going to have some work. So you probably could calculate the amount of energy that it gained or lost, the amount of work that was done, right? It was negative 60 at the beginning, and now it has negative 15, so that's like a positive 45 joules of work. There is an equation given to you on your equation sheet to help you do a little bit of a shortcut. Saves a few steps when doing these calculations. So instead of calculating the energy at each point, we're just going to calculate delta UE directly, and the equation is basically Q, so the amount of test charge multiplied by the change in voltage. So instead of having to do it at the individual voltages, all we care about is the change. A note on this equation, that Q is the test charge. So we still have not talked about where those voltage lines came from in the first place. We're only talking about the amount of charge that is in that point in space. So that Q would be the negative 3. And the delta V, of course, is the difference in potential from where we started to where we ended. Another synonym for delta V, since V can be called potential and difference means the same as change in, delta V is often referred to as potential difference. So if you see that particular combination of words, it means delta V. So if we use that new equation to calculate delta UE directly, we'll see that it's equal to -3, which is the charge of the test charge, multiplied by -15, because that is the change in voltage from where I started to where I ended. And when you do that calculation, you end up with positive 45 joules, which is the same answer we got when we took the longer method that we did first. So how do we calculate the potential at a location in space? How would we figure out what that potential should be if we didn't want to get out a voltmeter and measure it? Well, the voltage or potential, same word, remember, at any location in space depends on some sort of source charge that is changing that location of space, just like the gravitational energy around Earth depends on properties of the Earth that is creating this situation where objects can have energy in their force field. So there are two relationships that go into calculating what the voltage and potential at a location in space should be. There is a linear relationship with the magnitude of the source charge. So just like the gravitational field near Earth has a linear relationship with Earth's mass, the potential at a point in space increases if the source charge is very large. And there is an inverse relationship with the distance from the charge. So the equation shown on that slide lets me calculate the value of V, which is potential, as basically the source charge divided by the distance from that charge, and then multiplied again by Coulomb's constant, which is K, and we've seen that pop up before. That 1/4 pi E naught is 9 times 10 to the 9th on your equation sheet. A note about using this equation: remember that this time the Q in this equation is the source charge, so the charge that's generating the field, instead of the test charge that is being put into the field. And that R is just a distance in space from the source charge. So there doesn't have to be any object located at R. I could just find out what the voltage at that point in space is, even without a test charge. So this equation only cares about the source charge. There's no second object relevant in this equation. The way the signs are going to work in this equation is that positive source charges, so if Q is a positive value, distance is always going to be a positive value. So positive source charges are going to, by definition, generate positive voltages in the space around them. So this is like a picture of the equipotential lines around a positive source charge. You'll notice that all of those values are positive values, positive 10, 20, 30, 40, 50. And the reason those values get bigger when you get closer to the source charge is because there's an inverse relationship with distance, right? So the closer you are to the source charge, the more electric energy you're going to basically have, and that kind of should make sense. And another way to think about this is if you took a positive charge from an infinite distance away and you moved it to one of those locations, it would take positive work to do that. Or flip side, if you took a negative charge from infinity, it's going to be negative work to move that charge there. If I had a picture of a negative source charge, the equipotential lines around it would be negative values, because it takes negative work to move a positive charge there and vice versa. For some reason I had a hard time on the internet finding this like same picture of that I just put on the slide with a negative source charge, but just imagine everything is flipped and it would be a big negative in the middle and all those values would be negative, increasing towards the source charge again. So the biggest negative values are going to be closest to the source charge. Just note that if you moved an infinite distance away from this source charge, you would essentially have 0 volts, and it applies in that equation as well, because if you plugged a infinity in for R, the V basically goes to 0. So if you were interested in calculating the voltage an infinite distance from a source charge, it should be 0. If you have multiple source charges in your field of view and you wanted to calculate the voltage at a point in space within that field, the voltage is just going to be the scalar sum of the individual voltages. So this is easier than dealing with electric fields, for example, because for electric fields you had to both find the strength of the field and the direction of the field. When we're dealing with voltage or potential, you just have to find the amount and then add those things together. So if I had 3 source charges and I wanted to know what was the voltage at that location marked with the star, I'm going to use that equation that we just came up with on the last slide for each source charge. So the Q of the source charge divided by the distance away multiplied by that constant. So let's say we did that and we found that the voltage at the star from object 1, which is that positive charged object on the left, is positive 40 volts. And the voltage at the star from object 2, which is my negative object, would be negative 240 volts. And the voltage from object 3 is 80 volts. Then you could determine that the voltage at that spot marked by the star overall is negative 120 volts. It's just a matter of adding up the voltage contributions from all of the source charges. So as we talked about before, what this means that the voltage at that star is negative 120 volts, it means that if I took a random 1 coulomb charge that started an infinite distance from these other 3 charges and I brought it in and stuck it at the star, it would take me negative 120 joules of work overall to do that. It would release energy to do that. So that's what that value means. Of course, if the voltage was positive overall, then it would take positive work to put a positive object there. Let's take a little bit more detailed look at some equipotential maps surrounding multiple source charges. So if you had a system of charges that had 2 oppositely charged objects, a negative object and a positive object together in one point of space, you would find that the voltage near the negative charge is all negative voltage, and the voltage of the space near the positive charge is all positive. And that means that somewhere in between those charges, there's going to be a 0 volt line, a 0 volt equipotential line. And that line goes all the way to infinity. Okay, all of those other equipotential lines are not going to loop around back on themselves, but if we have opposite charges, there has to be a 0 volt line that goes all the way to infinity. And what that means is I could put a charged object anywhere on that line, even starting at infinity, and move it anywhere along that line, and it would take no work, because the amount of work done to get it closer to the negative object is the same as the amount, equal and opposite to the amount of work it takes to get closer to the positive object. A note about this: just because work along that line is 0 does not mean the force is not 0. The force actually is a value. It is definitely not 0 anywhere on that line. If you drew a free body diagram of either a positive or negative object on that 0 volt line, you'd realize that while the kind of up and down components of that force are going to cancel out, the negative object's pushing it to the side, and the positive object's going to have a sideways component as well. So the net force on an object is not 0, but the work is going to be 0, because the force is perpendicular to that equipotential line at all times. If you have 2 like charges in a region of space, they're going to make that whole region have a potential according to their sign. So that picture on the left shows what an equipotential map of 2 negative charges would be, right? It's still going to be like most negative near either of those charges. But what you notice is that there's always going to be an equipotential that kind of encloses them both, that makes the entire region the same sign. In this case, the whole region is negative because my source charges are both negative. So I wanted you to see the difference between an equipotential map of opposite charges, where we have this line bisecting them of 0 volts, and like charges where there is no 0 volt line except for at infinity, and the voltage is going to be entirely positive or negative in that region. The figure to the right of that actually shows the electric field lines and the equipotential lines. And one thing to note about this is that the electric field lines are always perpendicular to the equipotential lines, because of what I talked about in that last problem. Because if the force is perpendicular to the movement of an object, by definition, work is zero. So if you have either the electric field lines or the equipotential lines, you can draw the other one because you know that they're always going to be mutually perpendicular to each other. And we'll do some practice with that in class. The last figure I want to show you is a system of objects that has a couple charges that are the same and also one that is the opposite. So what you'll see there is, around those two positive charges, we have some equipotential lines enclosing the charges, saying that the potential everywhere in that space is going to be positive. And then in between the positive charges and the negative lines, one of those equipotentials shown is going to connect with infinity and be my 0 volt line. So the right half of the screen eventually will be a negative potential, and the left half of the screen will be a positive potential with a 0 somewhere in between. Okay, so I know this slideshow has been a lot already, but I want to provide one little graphic way of organizing some of this information that kind of helps me keep my brain wrapped around these 4 big variables and what similarities and differences do they have. So I made a table that basically has the type of variable on the left, so vector variables like forces and electric fields, scalar variables like energy and voltage, and then on the top of the table, how many objects are involved in those variables? How many objects do you need to have these variables? And what you're going to see as we work through this table is that E is related to Fe, so electric field is to electric force, as electric potential is to electric potential energy. So they're kind of like categories of variables that go together in a very specific way. So electric field, the equation for electric field has one Q in it because you only need one object to change the space around you with an electric field. And so that Q is going to be the source charge. And then when you want to bring a second object into that source field, then all of a sudden you can have forces between objects. You got to always have 2 objects to have a force. So in every equation for electric force, you'll notice there's 2 objects in there, Q1 and Q2. One can be the source and the other can be the test. It doesn't matter which one you put in which space. Same thing with this equation. There's 2 charges in there as well. It's a little harder to see, but Q in this case is my test charge, and E is the E caused by a source. So we have both of the objects in there. It's just that one is already represented by an E. We're going to see the same kind of trends when we look at our new variables. Electric potential at a point in space depends only on the object causing that warpage in space-time. And the equation is very similar to electric field. The only difference is an R versus an R squared. And that's because energy is force times distance. So it basically cancels out one of those R's. In any case, you'll notice that that Q is for a single charged object. So a single charged object can create electric potential in all of the space around it, regardless of whether there's another object. So that's Q as a source charge. But if I then bring a second object into the electric potential field that I've created with a source object, then I can store energy in that system, electric potential energy. So that's when I get my UE when I have 2 objects. And so in this equation for UE, we'll see Q. That Q is now the test charge brought into the space. And then the V is basically going to be the potential created by my source charge. So I have 2 objects again that can store up electric potential energy together in their configuration or in the movement of those 2 charges relative to each other. All right, so maybe you didn't know how big of a question this was going to be, but the essential question was, how do we store energy in the configuration of a system of charged objects? And this video is probably a lot like trying to take a drink out of a fire hose. Please just, wrestle with it a little bit on your own, and then trust that we'll do lots of practice with this stuff in class over the next couple weeks and months. Thanks for watching.